Everybody. Today we start a new unit, a new topic, so it's number 5 out of 7. However, I have to say that number 6 and number 7 are going to be really short. So this is the last comparatively long unit, and the remaining two will be much shorter. In this unit, we will discuss differentiation in general. That is, how to find the derivative, what is derivative, how to find the derivative, different methods, different rules of differentiation, different how to differentiate different derivatives of different functions, and all that. So basically, the techniques of differentiation. What does it mean to differentiate? How to do that? Different approaches, different methods for very special and sometimes more complicated cases. How to solve those? And then in the 6th unit, we will see how to apply what is the derivative useful, what is it good for. So in this unit, only the basics, that is the process of differentiation and let's say some very direct applications. And so here we are. Let's start. We will start with some very simple, very basic things. So where does the idea of derivative come from? So basically, the idea of differentiation starts from the 17th century. Calculus, in fact, calculus as a study of a part of mathematics, is a study of a process, a study of infinitely small quantities and infinitely large quantities. So that's where the name calculus comes from. Isaac Newton, the English mathematician, astronomer, physicist, wrote a work in Latin, which was called Calculation of Infinitely Small Quantities. And in Latin, the first word was, of course, calculus. So this is where the name of the branch of mathematics, calculus, comes from. And as Newton's, let's say, groundbreaking work indicates, it is dedicated to infinitesimal changes, to infinitesimals, to something infinitely small, maybe sometimes something infinitely large, but infinitely small changes, which altogether form a process. So calculus discusses processes, not necessarily always with respect to time, but basically a process. So if we consider a function or a graph of a function as a depiction of this process, then we might start to wonder, how do we investigate this process? So we will start with the gradient of a curve, and we will start with actually a very simple thing. We will start with a linear function. We know that for a linear function, what we have is the graph is a straight line, and we know that a straight line has a slope that is rise over run. So we have this straight line, which is probably, let's suppose this is the function y equals, I don't know, linear function kx plus b. And at a certain point, we want to decide what the slope is. But we know that the slope of a line is the same at all points. It's always the same at all points. So what we think is, all right, rise over run. So we create some run. We consider a run that would be a difference between two x values. Well, we can call the other one x1. And then here we see the run, or the difference between the function values y0 and y1. Respectively. And so, of course, the slope is rise over run. In fact, we could denote the difference between these two x values by delta x, in calculus, delta is a very common occurrence. Delta in calculus means basically we use delta, the symbol, to denote a difference. So delta x actually means a difference of x values. This would mean that x1 actually is considered as x0 plus delta x. In a few seconds, I will explain why we do this. And the corresponding difference between the y values, that would be delta y, the increment of the function. So the increment, that is the small increase in x values. So delta would be the difference, or we can also say the increment. Increment of the argument, increment of the independent variable. And similarly, dy, which is evidently y1 minus y0, would be the increment of the function. At x0, we say at x0, okay, this would be at x0, this would still be at x0 because the function depends on x. So at this point, so we say delta x. Why do we use this notation x1 equals x0 plus delta x? It's because x0 will be considered as the starting point. In principle, in further functions, you will see how this works out. So we generally, when we investigate a process, it's like determining your instantaneous speed when you are driving or cycling or walking. Instantaneous speed, what is that? If you move at a constant speed, then you take the distance you travel and divide it by the time, and you get your speed. That's your average, and at the same time your actual speed. And so at any given moment, we can do that. The speed is what I have at any given moment, even though we can find the speed, we can compute the speed only using a certain time interval. At a moment, just at a moment, the speed seemingly makes no sense because we need a time period in which we travel a certain distance. So that would be an analogy with physics, an analogy with even our everyday life. So this slope is like the speed at which you travel if your speed is constant at all times. And so we can write that this rise over run, or the slope of a line, a straight line, is delta y divided by delta x. This is nothing new. Maybe the notation is slightly different. We are introducing this delta thing, but in principle, this is nothing new. We know lines hopefully very well. So increment of the function value divided by the increment of the independent variable x. And we will say slope or gradient or instantaneous speed at the moment x0 or at x value x0. When we talk about speed, of course, if we travel at a constant speed would, of course, would be the distance traveled divided by the time period, of course. So this is something that we are used to. This is the simplest thing of all. So we have problem when the velocity, and now I'm saying velocity, not speed, changes. For example, at some time you might be traveling at 60 kilometers per hour, then you stop for a while, maybe you slow down to 40 kilometers per hour, start moving backwards, and we say, oh, now your velocity is negative because you're moving backwards. So something variable, something that changes at all times. So how do you define the speed, the instantaneous speed at that moment? How do you define the instantaneous velocity at that moment? Again, if you consider the distance traveled and the time period, it's the average. So how about instantaneous? the actual speed. I could say, okay, I traveled 300 kilometers in, let's say, 4 hours. So my average speed was 75 kilometers per hour. However, maybe I have been traveling at 75 at very few moments, at very short periods of time, and all the time my traveling speed, my traveling velocity is changing. And the same applies to functions. Here, for the linear function, the gradient or slope, these are synonyms. Gradient and slope is exactly the same thing. For the line, we generally call it slope. For other functions, we usually say gradient. It's the same thing. So colloquially, we might say it's the steepness of the graph. The slope basically measures the steepness of the graph. So how about other functions? Imagine another function whose steepness changes all the time. How do we estimate that? How do we estimate that? And so for other functions, for a general function, for example, tangent line is what shows the gradient. So suppose we have this graph of whatever function y equals f of x, some function y equals f of x. So this is a rather shaky curve, but I still try to draw it beforehand so that not to spoil the whole board on the spot. So the tangent line would show the gradient. So we choose the point. We are interested perhaps in the point x0. We want to know how steep this curve is. What is the gradient of this curve at that point? And yes, we can draw the tangent line and we say, okay, the steepness of the graph is this, the slope of this tangent line. The problem is that the steepness or the gradient of a general function changes all the time, just like your speed might change when you are traveling. So at x1, perhaps we have a completely different speed. So the speed, the gradient, and in this case, the gradient, the steepness of the graph is changing all the time in general, just like when you are traveling, your velocity changes all the time. So what do we do about that? Here we have the function again. And we think, all right, we are interested in the moment or the x value x0. At this moment, we want to know what the steepness of a curve is. The thing is, we are not doing it graphically. In general, this is the graphing illustration. The illustration with graphs is the easiest way to understand things. But in principle, we have a function perhaps given by a formula, given by an equation. Maybe we don't have any idea what this graph actually looks like. And then what do we do then? And so we would consider a certain point on the graph that is the function value at a certain x for certain x. And all right, let's try to do the same thing as with the line. Let's choose another time point, or for the motion, it would be another time moment, and the location somewhere else, like f of x1. So if I compare these two points where x is 0 and x is x1, I could still measure the run, which is still delta x. So x1 is still x0 plus delta x, as we can see. I can still see the corresponding change of the function, which would be delta y, which is function at x1 minus function at x0. Naturally, we could say this. And then we could actually draw the line through these 2 points on the graph and say, okay, that's the approximate, the slope of this line is the approximate gradient. Would this be a good idea? Probably not. As you can see, because we see how the slope is less than the slope of this yellow line at first, and then it becomes higher. It becomes greater for the actual curve. So the slope Maybe at one point of this curve, the slope is the same as that of the yellow line, but not nothing else. Similarly with speed and velocity, if you measure the distance you travel, the 300 kilometers, divide by the time period, 3 hours or 4 hours, then you discover your average speed, average velocity, just like here, you discover the average rate of change of the function. So we have actually a third word now. So in principle, we have 3 words for the speed or rate. Speed, which would be generally considered as the physical speed, so speed. Then we have velocity. Velocity is an oriented thing. Velocity in physics is a vector, not only the absolute value, which would be the speed. The speed is the absolute value of velocity, but also the direction. It would be in one dimension if we simply move along a straight line. It might be a vector in 2 or 3 dimensions, velocity vector. Its absolute value, its magnitude is the speed. So velocity is oriented. Velocity is not a scalar. Speed is a scalar, that is just a number. Velocity is not a scalar. Velocity always has a direction as well. And if we move along a straight line, that means it's positive or negative, perhaps. And the third word is rate of change. Rate of change, which is what we generally use for a function. So when we talk about a function, we mean rate of change. We say rate of change. The analogy for movement would be velocity. Speed, that's something completely different. Speed is the most primitive thing of all these. Velocity and rate of change have the same, let's say, complexity, even though velocity could be even more complicated. Okay, so I could, of course, consider rise over run. I could say, yes, that's, of course, delta y divided by delta x. That could be, of course, this f at x1 minus f at x0 divided by x1 minus x0. Yes, but that is only the average rate of change. That's the average rate of change. So how do we find the instantaneous at every different moment? What does your speedometer on your car tell you? How does that thing measure the velocity? Is it really always investigating the distance and the time period? There's something else. So we have a feeling that it's not only about distance and time. It's also something intrinsic about the idea of movement, or for the function, we could say the general idea of the current steepness of the graph. So what do we do about this? We could find another x1, so decrease delta x, and draw the tangent line through this point. Not the tangent line, sorry, the secant. The secant is a line that intersects the graph. Secant, another secant. We say, okay, now this looks a little bit closer to what we actually have at that point x0. So what if we decrease it even more, decrease the delta x even more, go closer to the starting point x0? Oh, yes, now it's even better. So the actual, this is in blue, the actual tangent line, which actually tells us about the steepness of the graph at this point, can be found if we decrease delta x. If we draw the secant, but we go closer and closer and closer and closer to the point x0. So that means delta x, if delta x becomes infinitely small. So what does that mean? Evidently, we have to deal with limits. And so we have the limit of the rise over run, which would be, of course, the limit when delta x tends to 0 of f of, and this x1, I will write, instead of x1, I will write x0 plus delta x. that would be this. So the function value after the change minus the function value before the change and divided by the corresponding change of x, which is delta x, of course. So that this limit actually is called the instantaneous rate of change. Okay. And slipped. And there we go. Rate of change. Instantaneous rate of change, but that would be the rate of change of the process, the rate of change of the outcome. It could be the rate of change, for example, the rate of chemical reactions. The rate of change of coordinate is, of course, the velocity, and so on and so on. So the instantaneous rate of change, that is depicted by the slope of the tangent line. The slope of the tangent line at this point, but this slope can only be found as a limit because we see the secant, the yellow lines, as we move along the graph closer and closer and closer to the point where the x value is x0. Of course, this secant line approaches this extreme position. The tangent line is actually the extreme position of the secant line. And the slope of this tangent line, of course, is the instantaneous rate of change, also known as the derivative of the function. In this moment, at this moment, it would be at the point x0. So basically, the slope, this rise over run limit, this slope has a value at every x0 point, at every starting point, at every x, it has a value. So the derivative of the function f of x, that is also the same as it's sometimes called the gradient function. It can be denoted by, for example, by f prime of x, which is actually a favorite, a preferred notation, unlike some of you who are used to writing only dy dx, which is not the best thing to do at all in all situations. We can write simply y prime, or y with a dash, means the same thing. Or yes, you can write d of something. You can write even the formula in there for the f function. You can write dy by dx. You can write d by dx of something, so the expression follows this notation. There are two different notations. This is the so-called Leibniz notation. Why Leibniz notation? That's because Isaac Newton worked in England, and at the same time, Leibniz worked in Germany, and they corresponded and they sort of competed. They were, you could say, inventing a new branch of mathematics, or in some ways, you could say they are discovering, because this is not an invention. We simply consider how things are, what seems logical, what looks like the thing in real world situation. So there's a lot of discussion going on among philosophers, mostly, not mathematicians themselves, but the philosophers mostly. Is mathematics invented or is it discovered? So are mathematicians simply people sitting in their offices or in their ivory towers, as they say, playing with numbers, playing with formulas, inventing things just for fun, for their own fun? Or are they actually discovering something about the reality, about the world we live in? So it all depends on how you look at it. There's no one correct answer to that. But what I was talking about was that Newton and Leibniz were at the same time, they were discovering the same things. Why did it happen at that time? Why did it happen at the same time? That's because you have to think at that time, probably scientists and people started being interested in processes. not in static things as this is that, you can compute this, you can use that formula, but in analyzing, understanding how processes develop, that not everything goes on smoothly. Things pick up speed, slow down, and so on and so on. So it seems that the civilization came to the conclusion that processes need to be investigated, and the value of the derivative, that would be the gradient, but we can say derivative at, so we can also say the derivative at the point x equals x0. We simply find the derivative of a function, it might be a formula, and then we just evaluate this at a point. It is possible to evaluate it directly, using this formula, using the first principles, using the limit, or it is possible to figure out the formula for the derivative and then put in the value of the point. So the same notation, just using x0, a specific number, instead of general x. However, if you don't use limit, if you use formulas, and you need to find the actual value of the derivative, then the rule is you first of all must find the derivative according to a formula, and only afterwards you put the x0 value into that formula. What else is there? Oh, there's one more thing, but that's in the next slide because there's more space in the next slide. So this is a ready-made picture from a book. See, the function is, the shape of the graph is somewhat different. In this case, you see that the tangent line is above the graph, and the graph seems to be, the function seems to be slowing down, becoming less steep. So the derivative of a function is defined in general for any value of x, of course, from the domain, as the limit of the increment of function divided by the corresponding increment of x. That is, we assume that we start at whatever point x we want. We may call it x0 if we are really interested in one and only one value of x, or in general, we could say at any point x, we increase x by some delta, by some delta x. We consider the corresponding change of the function, and we find the ratio. And then we consider the limit of that ratio as delta x becomes smaller, smaller, smaller. We should also note that the angle between a line and the x-axis, for any line, the angle, the tangent of the angle rather, the slope is the tangent of that angle. I will write this down in a few moments again. So in general, the derivative of a function is this. The more official definition from your lecture looks like this. Same thing. But see, for all x values from the domain, that's one thing, for all x values from the domain of the function, and the function has to be continuous in the domain. Basically, the points of discontinuity don't count. At discontinuities, we cannot find the derivative. At discontinuities, we cannot find the derivative. The derivative only exists where the function is continuous and not even always there. Not even always there, it happens, yes. So the function has to be continuous, that is, no gaps. Because as soon as there's a gap, how can we evaluate the speed, the rate of change of a function, if we have a gap there? Or if the function goes off to infinity, what do we say then? The speed, the rate of change is infinity? Well, you will see that sometimes we even do that occasionally. So the process is called differentiation. The process is called differentiation. So the derivative is this new function obtained from the old function, this derivative, this new function, characterizes the rate of change of this function. At the same time, it characterizes the steepness of the graph. So we could say it is instantaneous rate of change. Instantaneous rate of change. At the same time, it's the gradient of the tangent line or slope of tangent line. So what that means is that at any given point, if we draw the tangent line and the tangent line has slope, the slope is by definition, as we see, the derivative at this point, x prime, the f prime, derivative of the function at that point. That's the slope of the tangent line, as we saw so far. But please remember there's one more thing. It is also equal to the tangent of the angle. So let's not consider this the angle alpha. Let's consider the tangent line. If this now is the angle alpha, the angle that the tangent line forms with the x-axis, that angle, the tangent of this angle is the slope. Remember that was from the equations of lines in analytic geometry. So tangent of the angle alpha is the tangent of the angle that the tangent line forms with the x-axis. The slope that the tangent line forms with the x-axis is alpha. Then the derivative, the value of the derivative, actually is that tangent. We find it if we know how to find the derivative of a function, then we can find the slope and we can find the angle. The problem now is, so how do we find the derivative of a function? Do we really always have to do this limit? Well, the good news is no. There are standard derivatives. There are properties of differentiation. There are ways of finding the derivative of a function without having to do limits. We will only do this limit thing for a few examples today, and then we will have formulas, and then we will work with those. So differentiation, the process name, we don't say derivation, we have differentiation, to differentiate. The verb is to differentiate. And when we differentiate, we find the derivative of a function. The derivative of a function. That new function that is derived from the old function, but as a verb, we say we differentiate the given function. Okay. What else was there? I think at this moment nothing else. So the next slide, let's do some specific cases, some examples, some special cases. So let's have a look. Let's use now the definition for a linear function. Suppose we have this linear function. Let's check. So theoretically, at least from the first slide, remember from the first slide, the slope, the derivative of this linear function should be equal to k. It should be equal to k because we know that the slope of a line is k and it's the same everywhere. So let's just check it. So the derivative of this function would be, by definition, limit when delta x tends to 0. I'm going to repeat the formula, so that would be the function value at x plus delta x minus the function value at the given point or chosen point, divided, of course, by delta x. So just remember that the new point has x coordinate, x plus delta x. So we put that as a composite function into the given function. Instead of x, we put x plus delta x. So we are applying first principles now. We are applying the definition. Later on, you won't have to do this, but we will investigate just a few functions to see where it all comes from. Limit delta x tends to 0, so k times x plus delta x instead of x, then we have plus b, and then we subtract function normal at x. Subtract kx plus b. And divide by delta x, of course. That's all by definition. So we open the parentheses. Kx plus k times delta x plus b minus kx minus b divided by delta x. We see kx minus kx, they cancel out, plus b minus b, they cancel out. So we have limit k times delta x divided by delta x when delta x tends to 0. Now we see, basically, of course, if the function is continuous, why did we need the function to be continuous? For a continuous function, the very small change in x creates very small change in y, which means, evidently, we see the change of y is constant times infinitesimal. That is infinitesimal. So basically, this limit is 0 over 0, the indeterminate form, but fortunately for us, we can cancel out the 0 factors, and we see that the limit of this is indeed k. So the increment of x is infinitesimal when delta x tends to 0, that's it. The increment of the function in this process is also infinitesimal. So we have the ratio of 2 infinitesimals. We have to understand that. This is why the function needs to be continuous from the abstract formal point of view, so that we can evaluate the indeterminate form infinitesimal divided by infinitesimal. For the derivative, if the function is continuous, this will always happen. For continuous function, this will always happen. And we need to evaluate this limit in this way. So what this only means is that we see that when we increase the x value by delta x, we see evidently the function value increases by k times delta x. And of course, that means that the slope, the ratio, is just k. So for this, I could say that, for example, if I have a function, let's say 7x minus 5, derivative is simply 7, because 7 is the k value. So for linear functions, this is very simple. We look at the linear function, we look at the slope, and we say, okay, that's the value of the derivative for all values of x. That's for all real x values, for all values of x from the domain, and the domain is real numbers. Next one, let's take a quadratic function. Let's check a quadratic function again. So by definition, the derivative at any point x for this function is the limit when delta x tends to 0, so that's the increase of x. The delta x is in the denominator. Now the numerator, function value at x plus delta x. So instead of x, I write x plus delta x squared minus function at the old point, x squared. So we have, now we need to open the parentheses again. We have x squared plus 2x times delta x plus delta x squared minus x squared divided by delta x. A note here, a side note, delta x is considered as a single symbol. You do not separate delta from x. That's why I'm not using any parentheses. Delta x is a single symbol. It's as it is, delta x together. It's a single symbol because remember, It only meant that increment, that horizontal little segment. It's not delta separately. It doesn't mean anything at all. Delta of what? So delta x is the length of that small horizontal segment. Now let's see. X squared minus x squared disappears. Now we can take the rest. Now we can take the rest and perform division by delta x, evidently. So we have limit of 2x delta x plus delta x squared divided by delta x. And as we do this, we see limit of 2x dividing plus delta x squared divided by delta x is simply delta x. And of course, when delta x tends to 0, we have 2x. What this means is that x squared, the quadratic function, the derivative of the quadratic function is 2x for all x real values. 2x at whatever point you like. So this would mean that, for example, if we had the function itself, for example, if x is 1, then the derivative should be equal to 1. So let's say if f of x is x squared, so f derivative of 1 should be 2 times 1 is 2. This means what specifically? It means that the slope of the tangent line at this point, is 2. We can imagine, well, it looks like it is, so run 1/2, rise 2, for example. We can see that it looks like it. When we run this little distance, then the rise is 2 times higher for this red line, for this particular tangent line. If x is, for example, equal to 0, so derivative at 0 is evidently 2 times 0, this is times, is 0. What does that mean? That means the tangent line has slope 0. We know that the slope 0 means a horizontal line. The slope 0 means a horizontal line. So we can see that if a derivative equals 0 at some point, the derivative of some function. This means that the tangent line is horizontal because the slope is 0. Slope is 0, tangent of the angle is 0, means the angle is 0. So if the derivative is 0, the slope is 0, the tangent line is horizontal. When we move, derivative velocity 0 means we are standing still. So for motion, for situations of motion, 0 derivative, 0 velocity, standing still at that moment. It doesn't mean that you are standing still for a longer period of time. You can simply stop momentarily before starting movement backwards. That's also possible. So we could say, so we move with a positive velocity in the positive direction, then we stop and we start moving back. This means that at this point, at this moment, the instantaneous velocity was 0 because before starting moving back, we stopped. We didn't stay still any length of time. We started moving back immediately. What else could we see? We could also see, for example, for the same function, for the quadratic function, the derivative of, let's say, minus 1 is evidently 2 times negative 1 is minus 2. Yes, okay, let's suppose here, we see that the slope is negative. The function is, as you can see, actually decreasing. So this is already a hint of what is to come. We say that if the function is increasing, going up, the slope is positive. And if the function is decreasing, going down, the slope is negative. This is something that we will be discussing in great detail later on. For now, we discovered the derivative of a quadratic function. The derivative of the quadratic function is simply 2x for any value of x. At any given value of x, we can find the derivative, which actually indicates the steepness of the graph at that point. One more. Square root of x. Square root of x. All right. We will do the same thing. So the limit when delta x tends to 0. In the denominator, remember, we always have delta x. In the numerator, we have the function value at the new point, that is square root of, but the new point is x plus delta x. So it's like we have the graph, we take a step, we have with our point x, and we take a small step length delta x, evaluate the function value there. So x plus delta x, that would be at this point, the coordinate is x plus delta x. Delta x is actually the distance. So that's why we put x plus delta x, because we are evaluating the function at that point. The square root of x plus delta x minus square root of x. When delta x tends to 0, we see that this is again the indeterminate form 0 divided by 0. We should remember how to deal with these things, with this situation. We did it just yesterday. So if we have the radicals and the difference, we must multiply by the conjugate sum. All right, square root of x plus delta x under radical minus square root of x divided by the same x plus delta x minus root x. So now we can see that we have the limit when delta x tends to 0. We see it is x plus delta x without radical, because this is now squared, minus square root of x squared. Again, it's just x without a radical. In the denominator, we still have delta x, and we still have the conjugate sum. Sorry, this was the sum. This had to be the conjugate sum. I multiplied, for some reason, I multiplied by the difference. So here we have, this was the sum, this had to be sum, and then we could use the formula a squared minus b squared. Let's simplify. Limit when delta x tends to 0, x minus x disappears. We only have delta x divided by delta x times the conjugate sum. Now what happens is we can cancel out the 0 factor. And now if delta x tends to 0, then this first radical actually tends to square root of x. Square root of x plus square root of x is, of course, 2 square roots of x. Please note one thing. In all three examples, in all three functions that we did, x does not affect the limit. The limit is as delta x changes. So x, we say, okay, for any, let's say, specified x value from the domain. Suppose that x is a point from the domain in which we are interested. So we consider x as a fixed point. I'm simply not writing x0. X is a fixed point. At any given point x, we evaluate the limit as delta x tends to 0. Therefore, x itself does not change anything at all. We pretend that this is constant. For any given value of x, this will work, because delta x is what we change. Delta x is the thing that approaches 0. X is x. X is simply the point here which we are considering. The limit depends on this distance. And so we have now the derivative of the square root function as well. Square root of x derivative is 1 divided by 2 such square roots for all x values from the domain. Remember that the domain of the square root is like from 0 to plus infinity. but we cannot divide by x. We cannot divide by 0, I'm sorry. So this means actually not from the whole of the domain, excluding the starting point. We cannot divide by 0. So basically we would say no from the 0 point excluded to plus infinity. So for positive values of x. So if x is 0, we say that yes, evidently the derivative should be infinity. We cannot live without this. This morning I had an interesting discussion by email about whether a limit may be 0 or infinity. Yes, you see, 1 divided by infinity in this case is 0. If we have 1 divided by 0, we would have an infinity. So at this moment, when delta x tends to 0, it looks like we have the limit equal to infinity. Limit equal to infinity if x is 0. That means that there's no finite limit. That means that the derivative might not exist. A finite derivative does not exist. But we say, okay, infinity. If x is 0, we get the infinity derivative. What might that mean? We of course we have to wonder. Of course, it's something that needs to be thought about. And I wanted to change to white, and it didn't. White. Okay, just imagine the graph of the square root function. It's half of parabola. The tangent line at the 0 point is vertical. This is what the infinity derivative at this point means. There's no finite derivative. The derivative is seemingly not defined, but we understand that if we evaluate this limit, it's like infinity when x is 0, which means the tangent line has slope infinity. That is a vertical line. That is a vertical line. This is the peculiarity of calculus. We do consider these interesting divisions by 0. This is actually what happens. So the limit, when x is 0, this limit would be infinity. So the derivative value would be infinity, but it's one-sided limit because there's nothing on the left. So the left is the domain starts from 0. But at this point, we could think that the tangent line is vertical, which is what this infinity derivative at that point would mean. We will return to this. This moment is important. I wouldn't be wasting time discussing this, but this becomes important a little bit later. Okay, so some basic rules now. How to deal with this? Because if we have to do the limit every single time, it is really messy. It's really unpleasant. Next time, perhaps we could try also 1 over x derivative. 1 divided by x derivative could be done, but we shall see. At the moment, so the derivative of a power, so the first rule, if you have a power of x, then the derivative of this power, that is x to power a derivative, is, and some of you, of course, already know. I know that there are some people who have never seen derivatives before, but most of you have seen something of calculus at school, something of derivatives at school. So you'll probably remember it is a times x to the power a minus 1. That is, the derivative of any power function is a power function where the exponent becomes 1 less, but the old exponent goes to the front as if it is a coefficient. So the exponent becomes the coefficient in front, and the actual exponent decreases by 1. And the interesting thing is it is for all actually real values of a. For all real values of a. And of course, that would be for the domain for x from the domain of this function. Because evidently, if a is, let's say, for example, 1/2, it means the square root, right? The exponent 1/2 means square root of x. It only exists for non-negative values of x. So this means that we have to write not x's real number, but x from the domain, because different power functions might have domain all real numbers, only positive numbers, only non-negative numbers, and so on. Special cases. What this means, we already saw something. We saw, for example, that the derivative of x squared, that's something that is worth remembering, not doing every time specifically by formula or by limit, but just memorizing. This is something that we will be using ever so often. X squared derivative is 2x. It's used ever so often, but it's very good to remember by heart. Also, square root of x derivative. Now let's actually check. Square root of x is x to power 1/2. Derivative would mean take exponent as a coefficient in front, 1/2, times x to the power 1/2. Now subtract 1 from the old exponent. So we have 1/2 x to power minus 1/2. Remember that negative exponent means it goes to the denominator, elementary mathematics, and exponent 1/2, again elementary mathematics, means square root. So x to power minus 1/2 means divided by square root x. So we see that yes, it works. According to this formula, it actually works. So this is a special case. Again, I would suggest memorizing this as well. It's very good to know the basic ideas at once. So there's something else, of course, simply x derivative. X derivative, that's x to the first power, right? So this means 1 times x to the power 1 minus 1 is 0. X to 0 power is 1. So yes, just x derivative equals 1, another special case. Just x derivative equals 1. And now the very special case, the derivative of a constant. Derivative of a constant, if you remember this kx plus b derivative, if k is 0, 0x plus b derivative is 0, only the slope. So constant, it doesn't matter what b is, what the constant b is actually. So this means that the simple plain constant derivative is 0. That's the special case. This is the special case. I wanted to write it higher up, but somehow I started with those other derivatives. So x derivative is 1, x squared derivative is 2x, square root of x derivative is 1 divided by two such square roots, constant derivative is 0. Well, there might be something else, for example, 1 over x derivative. We will not do it using limits, so we could do it x to power minus 1 derivative, that's this one, is minus 1 times x to power minus 1, subtract 1, minus 1x to power minus 2. Power minus 2 means square in the denominator, minus 1 over x squared. Again, something that is worth remembering, because these are the actual derivatives that we will see a lot. This is something that is very useful to remember, because if you have to do this process every time, it takes up too much time. It's long, it's slow. So best of all is the best thing to do is to memorize at least some, not everything, but definitely this would be a very good idea to memorize. This would also be a good idea to memorize, because we will see a lot of square roots. This absolutely, and this absolutely. And of course, remembering this kx plus b, which was something that we saw at the beginning. Now, that's the first basic rule. Now, the derivative of a multiple of a function, that is k times, so constant factor times a function. If I know the derivative, for example, of the x squared, do I know the derivative of the function, let's say 7x squared? Yes, we do, because this second rule, so the first rule was derivative of a power rule, you could say, derivative of a power, how to differentiate a power. The second rule is how to differentiate function times constant, multiple of a function. Easy peasy. We use the same constant and apply it to the derivative. We simply take the constant outside. So that's in general. This thing can be proved using the limit laws, using limit properties. Limit properties would allow us to prove that this is true. This works for all functions. If a function can be differentiated, if the derivative exists, then this function times a constant differentiated is the derivative times constant. So we simply can take this out in front. So, and the derivative of a sum or difference of two functions, again, using limit properties would be the same. So if I have function f of x plus or minus another function g of x, and they both can be differentiated, this means you can differentiate them separately and add, subtract afterwards. So f derivative plus or respectively minus g derivative. Note that I am not using Leibniz notation here. I'm not using the notation d whatever by dx. Because this is basically, you see, it's more writing. It's much easier to just put the dash to denote the differentiation. It's much easier. There are other reasons why I don't like this notation particularly. I will come to those a bit later. Probably not today. There are situations where this notation actually is useful. For example, next time when we discuss chain rule, that is how to differentiate a composite function, then this notation will actually be very useful. This notation also has several special meanings. It is useful, for example, for integral calculus, things that you will be doing next semester, integration. It's important that you are, of course, familiar with this notation, because this will be very, very important there. Mostly, we will have a couple of applications where this notation is more useful than the dash notation, this prime notation. However, on everyday basis, we will be using the prime notation because it's much faster. I have the function, put it in parentheses if it's a longer formula. Prime means now differentiate. You have the function, now differentiate. This notation actually would mean differentiate and only then giving the function. In this case, you see, this is the function, now we differentiate it. So the order of thinking, the sequence of thinking is reversed. However, it doesn't hopefully detain us. All right, example time, practice time. So those of you who have done differentiation before evidently will be able to do this hopefully easily. So, all right. I will do 1, 2, 3, 4, 5. First of all. So let's see. We don't write equals because it's not, the function is not equal to its derivative. You can write, for example, y derivative equals, now you should be able to see, 3 becomes a coefficient, and the actual exponent is 1 less. 3 minus 1, that is 3x squared. Actually, I do not expect you to write this 3 minus 1. You should be able to see immediately that it has to be x squared if we decrease the exponent by 1. Of course, it becomes 2. I would say that's obvious. So in principle, I would expect in a general situation you to be able to write very quickly and immediately this. That's nothing really difficult. X to the 12th. So similarly, we could say y derivative is 12x to the 11th. 12 becomes the factor in front, the coefficient in front, and the actual exponent becomes one less. Now for this third function, it's a linear function. So remembering the linear function, we of course remember that the slope was 0.6. The derivative is 0.6. 0.6. Or you could also remember that x derivative is 1. So 0.6 times x derivative is 0.x. And 2 derivative, constant derivative is, of course, 0. That's something that might be noticed. Next one. F derivative is, now 5 is a constant k, so we leave 5 as it is, times x to the 6th derivative would be 6 becomes another coefficient times x to the 5th power because the exponent decreases by 1, minus next 1/2 x to the power 10 derivative is 10x to the 9th power plus next 13 is the constant coefficient. X squared derivative is 2x. Something to be remembered? Fine. X derivative, simply x derivative, is always just 1. What about pi square derivative? It's 0, because this is a constant. It's 0, yes. This is a constant. This is a constant, and therefore this is 0. We generally, you don't have to write it. I am simply pointing these things out for those people, not too many, but there are people who have never done things like this before. So I'm trying to go comparatively slowly. 30x to the 5th minus 5x to the 9th plus 26x plus 1. And again, I have no doubt that most of you will be able to write this immediately at once. Look at the function, write the derivative immediately. I was doing it slowly to illustrate what we do, or rather how we think for this, what is our way of thinking for this. But in practice, I would expect you to be able to do this as soon as you see f of x. It's a simple polynomial. Okay, polynomial differentiation is very, very easy. In this case, h of x, we would have 0.1 times minus 4, so it's minus 0.4 times x to power minus 5, because minus 4 minus 1, be very careful when subtracting 1. It's a very common mistake to think it's minus 3. It's minus 5 because you subtract from a negative number. Plus 8 times 2.5 would be 20, x to the power 1.5. In this case, I don't have to change anything to transform anything. The negative exponents happen. Of course, if we have an example given in the radical form or as a fraction, then we should write the answer in the same form. That's more or less. So let's see. We have two more, which means I should. Well, all right. I will be forced to erase this a little bit later. So two more examples. So for this, first of all, let us transform the function so that it becomes easier to differentiate. So it is 4x cubed minus 2x to the power minus 2 plus x to the power 2/3. See why we needed to discuss exponents very carefully and radicals very carefully in elementary mathematics. To be able to do this, without this transformation, you would not be able to differentiate. So y derivative will be x cubed derivative, remember 3x squared, so it's 12x squared. Now, minus 2 from the exponent, it becomes an extra coefficient. So minus 2 times minus 2 becomes plus 4. X to the power minus 2 minus 1 is minus 3. Very careful again when subtracting. Again, there's nothing to stop you from doing this or from doing this actual subtraction thing, writing it down, at least for those people who are completely new to this. I know that not all countries include differentiation in the high school curriculum. And now the last one, plus 2/3 x. 2/3 minus 1 is minus 1/3 when we decrease by 1, which means we have, yes, 12x squared plus 4 divided by x cubed plus 2/3. And now this is the cube root of x, but because it's minus 1/3, the cube root of x is in the denominator. Cube root of x. Please be very careful when you write numbers like coefficients and when you write the root index, so that it's clearly visible. The root index 3, it's write it inside the root so that it's very clear what is going on. So this is the derivative of our y function from this. Now finally the g function, I will okay, I will simply do it in a different color. Okay, I am taking this away from there to there. And now for the g function. For the g function, yes, it can be done using the chain rule, product rule, quotient rule. For now, so if you have forgotten those, for now, I could do this. I could open the parentheses, that is, apply the formula for the square, which means x to the 6th minus 6x cubed plus 9 divided by x squared. This means my function becomes x to the 4th divided by x squared minus 6x because I divided cube by x squared plus 9x to the power minus 2. When I divide 9 by x squared. So the derivative of this function will be 4x cubed. 4 becomes the coefficient. 4th power becomes 3rd power, decreased by 1. Minus 6x. Derivative is simply minus 6, because x derivative was 1. And 9x to the power minus 2. 9 times minus 2 is minus 18. X to the power minus 3. Minus 2 minus 1 becomes minus 3. So once again, I can write 4x cubed minus 6 minus 18 over x cubed. If you want to write this again on the same line, you may. It's not strictly required. I am not requiring it, but if you prefer this form, and I know I have seen people who actually do like to write things on a common denominator, so it would be 4x to the 6th power minus 6x cubed minus 18. Yeah, that's possible. We can write it like this, and then, well, if you want to take 2 in front of the parentheses as a common factor, you may, but there's absolutely no need at the moment. The thing is that for practical purposes, we will quite often actually change the final answer, the derivative, in the simplest form and factorize it. It will be necessary. In many cases, it will be necessary to factorize it, to simplify as much as possible and factorize the derivative. For now, so we have had 1, this was the answer, 2, this was the answer, 3, this was the answer, 4, this was the answer for 4, 5, this was the answer, and then we have 6, this was the answer, and finally, number 7 with this, or this is an answer. So we have had quite a few examples. Now I do have some more. And we will do, well, we have something like 16 minutes, exactly enough, I think, or I hope. So this, okay. So in order to differentiate, the first rule is, first of all, let us change the function into a more recognizable form for differentiation. Yes, you might not want to change square root of x if you remember the derivative of square root. If you remember the derivative of square root, it's 1 divided by 2 square roots of x, that's fine. That's simply fine. We can work with that. So we could say x to power 1/2 plus 2 times x to power. It's in the denominator, so exponent is negative. It's cube root, so it's minus 1/3 plus square root of 2. It's a constant, which means its derivative will be 0. So the derivative of square root of x is 1 divided by 2 such square roots of x. Or, yes, if you have difficulties, you can, of course, every single time you see a square root of x, do this. 1/2 x to power minus 1/2, and then transform. Absolutely no need. If you remember this, then it's fine. Now, next term, minus 2/3, because we multiply by minus 1/3, x to the power minus 1/3 minus 1, minus 1/3 minus 1, that would be minus 1 and 1/3. And of course, plus 0, constant derivative is 0. So we can actually simplify this some more. So 1 divided by 2 square roots of x minus 2 divided by 3, x to power 1 and 1/3. So x to power 1 is x to power 1/3 is cube root x. And that's it. That's the derivative. Absolutely no need to combine these on the same line at the moment. We can leave it as the sum of two radicals. There's also no need to eliminate the irrationality, the radical, from the denominator. Again, something that is not required for functions. So in principle, for now, this is perfectly fine. The next one, well, if we just understand that this middle term is minus 2y to the power minus 3, negative exponent, then writing z derivative, the derivative of this function is, oh no, there's one more thing. Z is y cubed divided by 3. Note that this simply means 1/3 times y cubed. And then, of course, we have 1/2 times y. It seems very obvious to me, but I forgot that it's not so obvious for every single person here. All right. So I have changed this function. I have rewritten this function altogether, all terms. So if I divide by a constant, I can always write it as times a fraction, because that will help us differentiate. If you have the constant in the denominator, we might have a problem. So we have 1/3 times y cubed derivative is 3y squared minus 2 times y to power minus 3 derivative is minus 3y to the power, careful, minus 4, because minus 3 minus 1, subtraction, plus just 1/2, because y derivative, if y is the independent variable, so note one interesting thing. In this case, y is the independent variable, and z is the function value. So we have to be careful. So we consider y the independent variable, and therefore we differentiate with respect to y. There will be some more complicated situations later, not today, but this is something we need to know. And that means the answer is y squared plus 6 divided by y to the 4th power plus 1/2. And that's it. That's the derivative of this z function. I know that some people would really want to use the quotient rule or the product rule. In this case, actually, it would be too complicated. In these cases, no, it's really too complicated. Best if you can change to the derivative differentiation of powers. Do that because that is so much more easier to do. Otherwise, the more complex method you are using, the more opportunity for you to make a mistake. We don't want that. So basically, if you can do it simply, do it simply. Only use the complicated methods if there's no other way of doing it. All right, some more. Again, let's change the u function. The u function is now 1/2 s squared. So now the independent variable is s. We have the function u of s. 1/2 s squared minus, very careful, 2/3 is the constant, and s to the power minus 2. Separate constants from variables. That's a very good thing to do because that will help you to do this more easily. So plus 1/4 times s to power minus 1. Because if you don't do this carefully, if you do this wrong, then you will basically get the wrong derivative. So separate the constants and be very, very careful with those negative exponents. So basically separating a constant is essential because otherwise you might actually come to harm, or your derivative will come to harm. So now the derivative of the u function with respect to s. Also, this is the case where we might want to write du by ds. One of the meanings of the Leibniz notation, one of the good uses is, for example, if we don't have the regular form, y is a function of x, but we have other names for the variables, then using that Leibniz notation indicates that you understand which is the independent variable, in this case s, by which we are differentiating by s, and which is the function value, which is the dependent variable, in this case it is u. Simply to indicate that, yes, we understand we are differentiating the function u by the independent variable s. It also works when we have functions with several variables. We will have them in the 7th unit. Not only y is a function of x, but sometimes z is a function of x and y, or worse, or more variables. And so now, differentiating 1/2 times derivative of s squared is 2s minus 2/3. This is s, this is not a 5. 2/3 times minus 2, s to the power, again, minus 3, minus 2, minus 3, minus 1, plus 1/4 times minus s to power minus 2, if you don't remember by heart. And so we have simply s, then we have plus 4/3, s to power minus 3 means s cubed in the denominator, and here we have minus 1/4, and s to the 2nd power goes in the denominator because the exponent is negative. And again, yes, if you like, you may write this whole thing on the same line. What I would not advise to do, I would not advise to write the given function on the same line, because then you will be forced to use the quotient rule, which is for the next time, which is for Monday, actually. Today, we are not considering quotient rule or chain rule, because those are again different, those are more complicated somewhat. So we are using only the simplest methods today. But if you want to write the function on the derivative on the same line, you may. 12 s cubed will be the common denominator. Multiplied by 12 s cubed, we will have 12 s to the fourth. Multiplied by 4, we would have just plus 16. Multiplied by 3s would be minus 3s, if you like. If you like. This is not strictly necessary. This is not strictly necessary. I would accept this. I would accept this answer. Let's see how much more do we have. Oh, these are more complicated. So for these, evidently, I will only rewrite before differentiation. You can do them by yourselves because you see, this is the exercise from your lecture transcript. After the lecture, in just a few minutes, I will upload the 5th unit. You will be able to see all the exercises and all the answers for this particular lecture for this type. So we have 1/6 is the constant because we divide by 6, t to the power 3 over 4. Remember how we translate radicals to exponents. Minus 1/5 t to the power evidently negative 5 plus 1/2 t to the power negative 1/2. It's in the denominator. This is the x function. So we are differentiating function x in terms of t. So we have to write dx differentiated by dt, and you can do that. You can do that independently at home or in any other way. So sometimes. And these last two things, what I would do, I would very definitely perform division. I would not want to do this as the quotient rule. Some people would like to do it. Actually, it's much easier if I perform the division. Okay, back. Keep and from current slide. For some reason, I moved too quickly. So I would divide. So I would see this is 8 divided by 2 is 4. Exponent 4 divided for x to the 4th divided by x to the power 1/2 would be x to the power 3 and a half, because I divide power 1/2 out. Minus 4 divided by 2, 2. Dividing by square root of x, I simply have x squared remaining. And 1 divided by 2 square roots of x is 1/2 x to power negative 1/2. And then y derivative can be found again as always, applying the same old rules. And finally, in the final case, my very strong advice would be, again, open the parentheses and simplify the function before you do anything dangerous, because otherwise it becomes really complicated. X to the 4th minus 6 x squared times square root x plus 9x, opening the square, dividing by x square root x. I am not differentiating yet. In this case, I have not differentiated. In this case, I will not differentiate. I will leave that to you. I'm simply reminding you what you should do. So 4, and this is exponent 1.5, 1.5. So 4 minus 1.5 is x to the power 2.5 or 2.5. Minus 6, x cancels out, square root of x cancels out, just x remains, and plus 9, 1 divided by x to power 1.5, that would be x to power minus 0.5. So very, very carefully, if you need more time to understand this, to follow this, you can do that on your own at home. But I would say that correct transformation sometimes of the given function is the key for easier differentiation. If well, those of you who know quotient rule, chain rule, product rule, want to do this using those rules, you may find that in many cases it's not simpler. In this case, it depends. It depends, probably. You would still need for the quotient rule. No, you would. No, it's less pleasant. It's less pleasant if you use the quotient rule for this. Definitely so. So for now, we are just using the power rule. So powers, derivative of the power. This, some derivatives that we discovered, we know already, we might know by heart. And of course, multiple of a function, how to differentiate the multiple of a function, and the sum or difference of two functions. So at the moment, we have 3 rules. Next time, 3 more. All right, so I will see you on Monday. That's just in 2 days, the day after tomorrow. But all right. So next time, Monday, this very same time at 10:15. And we will look at more rules, that chain rule, product rule, quotient rule. So how to differentiate a quotient or a product. At the moment, please note, no, you do not differentiate these separately. You do not differentiate the denominator and numerator separately and leave them where they are. That would be incorrect. If you see a product of 2 polynomials, again, no, we do not write first polynomial derivative times second polynomial derivative. Notice, we have the rule for sum and the difference. We do not have a rule for the product of 2 functions or for the quotient of 2 functions. Those will come up next time, just in 2 days. So don't use the rules we do not have yet, because in many cases there's a danger of doing it completely wrong before you have learned how to do it. Some of you do know, I'm sure of that, but the rest, please do not try to apply multiplication, division directly. Don't try to differentiate product as it is directly. Transform, differentiate it as a sum difference. Next time, you will see how to differentiate the product. All right then, I hope everybody has written their name in the chat. And I'll say goodbye till Monday. Goodbye.